Okay, so my pleasure to introduce the second speaker of this afternoon's session, Mr. Catalan from Barcelona, and I'll just let him take the floor. We've been pretty informal about, ask the questions during the talk, and I'll let you know if we get going too long.
So thank you very much, and good afternoon to everybody. I'm supposed to give you an introduction to oxide ferroelectrics that lasts about 90 minutes. 90 minutes is a huge amount of time for me to be talking. At the same time, it's probably not enough to cover everything that should be covered. So if I don't get to the end of my presentation, it doesn't matter. What should matter is that whatever I do talk about is understood by you. So at any point, feel free to interrupt me, and let's make sure that before I move on, you understand what I've said, right? I've broken my talk into several blocks anyway, so there will be pauses for asking questions. Right, the title was Introduction to Ferroelectrics. I've added to oxide ferroelectrics to make it relevant for this audience, and also to emphasize the fact that ferroelectrics don't need to be oxides. And quite a few of the things that I'm going to say in my talk are specific to oxide ferroelectrics, but not necessarily general for all ferroelectrics. Right? I should really emphasize that because ferroelectrics can be also fluorides. They don't even need to be ceramics, they can be plastics. There are plastic ferroelectrics like PVDF. So I would not want you to get the impression that the only ferroelectrics are perovskite ferroelectrics. Okay? So in fact, with that, I've already covered my disclaimer. Not all ferroelectrics are perovskites. Okay. Good. And yeah, I've structured my talk into 4 kind of blocks. First, I will try to cover the basic ideas of ferroelectrics or perovskite ferroelectrics and some of the applications. And I emphasize again some because ferroelectrics have a huge amount of applications. And in particular, as well as all the electronic applications that I will talk about, we also have optical applications. And I'm not even going to talk about the optical applications of ferroelectrics, but actually I think by market share or in terms of how many grams of ferroelectrics are devoted to applications, I think optics is probably the biggest application. I will also talk about experimental measurement of ferroelectricity, and this is perhaps the most important and useful thing that I will explain today. This is the kind of stuff that I wish someone had told me before I started playing with ferroelectrics, artifacts. Okay? If you ever go into experimental ferroelectricity, you will inevitably encounter some artifacts, and it's better that you know before you publish them. Okay? Then, if I have time, I will talk a bit about the basic Landau theory of ferroelectricity, which is particularly relevant with regards to the coupling between polarization and strain, which is piezoelectricity. But it's also important because it's useful to understand the concept of strain engineering. You can use strain to modify the properties or the symmetry of ferroelectrics. And finally, if I have time after all of this, I will talk about some trending topics, things that are fashionable right now in the area of ferroelectricity. Okay, before we even start, in case somebody here doesn't know what a ferroelectric is or what a perovskite ferroelectric looks like, this is a perovskite unit cell. We've seen it this morning. The perfect perovskite unit cell is perfectly cubic, centrosymmetric. Some perovskites, when you cool them down, they become polarized. What that means is that the center of negative charge of the unit cell, which would be the center of the octahedron, does not coincide with the center of positive charge, which would be wherever this ion is. Okay? So you have a dipole. That's a very simplistic view. Instead of off-centering here, you could off-center the octahedron with respect to the A side. I'm not even going to talk about that. But the basic idea is that there is an off-centering of the ionic sublattice with respect to the oxygen sublattice. So you get a permanent stable dipole, which, very importantly, you can switch with a voltage. So if I apply voltage, I can make this ion go from being in the top of the octahedron to be in the bottom of the octahedron and stay there. Okay? Which means that you can use it for ferroelectric memories. I will go into this in a second. In between the high temperature paraelectric phase and the low temperature ferroelectric phase, the material doesn't quite know what it wants to be, which means that it's extremely susceptible, and so its susceptibility, its dielectric susceptibility, goes through the roof. It really goes up. You have a very, very highly polarizable unit cell, and you have a very high dielectric constant, which is also very useful. Okay? White perovskite oxides, I don't even need to cover this because you've seen it this morning. It's a very simple structure within which you can get almost any property you want. And any property you want release any property you want. Okay? Ferroelectrics, multiferroics, colossal magnetoresistance, high temperature superconductors, mod materials, materials with a metal insulator transition, you name it. I'm yet to encounter something that has not been found in perovskite ferroelectric or in perovskites. And in particular, it seems to be the case that in perovskites you tend to have the record for any of those properties. So the highest temperature superconductors, the highest temperature multiferroics, the best piezoelectrics, and so on and so forth. So it's a very exciting family of materials. Okay. This morning someone was asking about how to use ab initio calculations or per principles calculations to predict whether a material is going to be stable or not, and which properties are going to have. I am not a theorist, so I cannot tell you about this. I am also not a solid-state chemist, but I do know a little bit, enough about solid-state chemistry to tell you how, let's say, first principles calculations used to be done in the prehistory, which is still useful. Okay? And the first consideration is geometry. Okay? If you want to make a perovskite unit cell, you need the distance between the A side and the oxygen to be square root 2 times the distance between the oxygen and the B side. Okay? So if the size of this ion and the size of this ion and the size of the oxygen are such that this thing is fulfilled, so that this divided by this gives you 1, then you should have a perfect perovskite unit cell. Strangely enough, well, because this conjunction of sizes is very rare, it happens very rarely that something would be a perfect cubic perovskite, right? But it does happen at room temperature. Strontium titanate is cubic. At very low temperatures, it's not. Barium zirconate is also cubic, I think, at room temperature. And many other materials at high enough temperatures can be cubic. Everything at high temperature is more symmetric. Generally speaking, though, when you cool down, the sizes will not give you this perfect tolerance factor equals 1. This is called the Goldsmith tolerance factor. This guy called Goldsmith lived at the end of the 19th century, I think. Now, if T is bigger than 1, that means that this, this cage, the A side cage, is very big. The distance between, which means that there's a lot of empty space for this B side for this B ion to rattle. It can rattle in any direction, and so you have a very polarizable unit cell. So if you have T bigger than 1, but not too big, because if it's too big then it's not even a perovskite, but it's close enough to T equals 1, but a bit bigger than 1, then you have a favorable situation for ferroelectricity, a geometrically favorable situation for ferroelectricity. And if T is smaller than 1, then you have basically this cage is too small, the octahedron doesn't fit, and in order to fit it has to rotate and tilt. Okay? And this in fact is by far the most common thing in perovskites. Most perovskites at room temperature are tilted octahedral systems rather than ferroelectrics or cubic. Okay? So that's the first consideration, is pure geometry. And that can take you so far. Then there's a couple more considerations to do with chemistry. And I emphasize I'm not a solid state chemist, but what I'm going to say is widely accepted. I suppose nobody will challenge me, but feel free to challenge me if it doesn't matter. Okay, so for polarization to happen, you want this bad boy here to go towards one of the oxygens. So you want them to hybridize. Well, that's one of the situations in which you can have polarizations. For that to hybridize with the oxygen, one way in which this is facilitated is if this transition metal atom has the d orbital empty. If there's electrons in the d orbital, then there's electronic repulsion between the electrons in the d orbital of this and the electrons in the oxygen. So it's not going to move towards the oxygen. But if it is empty, then the hybridization happens more easily, and so this will shift towards one of the oxygens. Okay, so this is what's called D0 polarization, and that happens if you have titanium in a 4+ state. The last occupied state is actually not an occupied state; it's an empty d orbital. Okay, and that would be the case for ferroelectrics with this kind of ions: titanium 4+, zirconium, niobium 5+, tantalum 5+, so on and so forth. there's another kind of polarization that can happen, whereby instead of off-centering this, you off-center the A side with respect to the oxygen. And for that to happen, one thing that people have found out that is quite favorable is to have this A side with the last electronic orbital being an S orbital with 2 electrons. And that's what's called a lone pair. A lone pair has spherical symmetry, so these 2 electrons can move in any direction they want. And that basically makes for a very polarizable atom. And so with these tricks, plus the obvious consideration that the unit cell has to be neutral, you can have these kind of combinations of atoms that will give you a ferroelectric. Okay? So if you have 3 oxygens that have -2 electrons each oxygen, you have a negative charge of -6. Then the A plus the B side have to have +6 charge, and so you can have +1 on the A side, +5 on the B side, or +2 on the A side, +4 on the B side, and so on and so forth. And these are some typical perovskite ferroelectric combinations. Okay, so lithium niobate, or barium titanate, or lead titanate, or bismuth ferrite, which is a classic one. I put bismuth manganite with a question mark because I think to this day nobody has agreed as to whether it's ferroelectric, anti-ferroelectric, or neither. For reasons that are it's irrelevant. Point is, there are all these tricks that solid-state chemists have been playing for a long time in order to guess what materials would be ferroelectric, and for the most part, they've got it right. Okay? Right. So if you don't want to do your first principle calculations, you can start with this. If you don't want to go deeper, then you speak with a good first initial, theoretical physicist, and they can give you additional considerations that I can't. Okay. That's from the point of view of chemistry. From the point of view of let's say physics or solid-state physics, or I don't know what would be the point of view of this, you can think of ferroelectricity as a lattice vibration that is polar and that gets frozen, right? So this is a classic perovskite transverse optical phonon, and as you can see in these vibrations, the oxygen lattice is off-centering with respect to the cationic lattice. Okay. At high temperatures, as long as this is vibrating around the center, this is centrosymmetric. As you cool things down, this phonon gets slower and slower and slower, and eventually it freezes. And when it freezes in a polar position. Okay. And this actually is a good trick to try and identify ferroelectricity in materials that are normally very conducting. Okay, this example, in fact, is good because this is not an oxide. It's lead telluride and lead germanium telluride. These are half metals or semi-metals. These are basically very conducting. If you wanted to measure a hysteresis loop on this, it would be difficult. However, if you look at the phonon spectrum, you see that, okay, this phonon never freezes. It is the frequency of the phonon. It's a function of temperature. This transverse optical polar phonon, for this composition, never freezes, so this is never going to be polar. But as soon as you mix it with germanium telluride, there's a finite temperature where things do freeze. Okay? So at least it's polar. Whether or not it's ferroelectric, then it becomes a bit of a semantic question, because the standard definition of ferroelectricity is that something has to be switchable. The polarization has to be switchable, and if the material is very conducting, it's not trivial how to switch it. But, okay, at least it's polar. Questions? No questions yet. Don't worry, I'm going to make it even scarier. So I've been talking about this phonon freezing. One interesting thing that can happen, and this is not something that you need to know, but I find it quite exciting, so I'm going to tell you about it, is that if the phonon frequency freezing, so if the phonon freezing happens at a temperature very close to 0 Kelvin, right, phonons have a certain momentum, okay, they have a certain momentum. If a phonon freezes, you will know at the same time its momentum, which is 0, and its position, because you know the atomic position. At 0 Kelvin, you know that quantum mechanically you cannot know exactly both things. There's a certain, if you multiply the phonon momentum by the position, that is basically the Planck's constant. So that is to say, if the phonon freezes very close to 0 Kelvin, this quantum fluctuation, this quantum indetermination, if you want, is sufficient to prevent the phonon from freezing completely. And that's what happens in a material that is probably very familiar to you, which is strontium titanate. Strontium titanate would like to be ferroelectric, but it just so happens that its ferroelectric critical temperature is so close to 0 that the phonon cannot freeze due to quantum fluctuation. Now there's this very exciting experiment whereby you can substitute the oxygen atoms in your STO by oxygen 18. So instead of oxygen 16, you use oxygen 18. Oxygen 18 is heavier, and because it's heavier, the phonon freezing happens at higher temperatures, so it can actually freeze before it enters the quantum region. Okay, so just by changing the weight of the oxygen, you can turn something from being paraelectric, what they call actually a quantum paraelectric, into being ferroelectric. And this, I don't think I will get into that, but this is one of the trending topics now in ferroelectricity. If you want to go into fundamental physics, quantum ferroelectrics are a fashionable thing, or a trending topic, if you want.
I had a quick curiosity on how are these substitution of oxygen made in practice?
With great difficulty. So I have never done it. I think oxygen 18 is extremely expensive to combine. These experiments are, the only group that I know that does it is a group in Japan led by a guy called Ito, I-T-O-H at the end. And I don't know who is his supplier for oxygen 18.
But are thin films or crystals?
No, these are single crystals. So you take a single crystal,
So it means that it has to be
you anneal it.
atmosphere.
Yeah, exactly. You put in a capsule, you anneal it in oxygen 18, and then you measure it, and it works. It's quite amazing. I think one of the great things about oxygen 18, well, great and not so great, is that it's radioactive. Right? So it's not an easy experiment to do, also because of that reason, but because it's radioactive, it's easy to quantify. Quantifying oxygen is extremely difficult. It's one of the great practical challenges in perovskites. But with oxygen 18, you know exactly how much you have because it glows in the dark. So okay, so quantum paraelectrics is an almost ferroelectric kind of family of materials. Another almost ferroelectric. Yeah, sorry.
So as you mentioned about the oxygen effect, right? So how about the A side strontium effect?
It has been, yeah, that has been done. So you can, if you want to do this experiment more cheaply, what you do is you substitute the strontium by a tiny amount of barium to make it bigger, or calcium to make it smaller. And either of them will work to turn your material into ferroelectric. It's just less cool, like but yeah, it does a trick. Yeah? Okay, so quantum paraelectrics, of which STO is the most famous example, is one family of almost ferroelectric materials. Relaxor ferroelectrics is another family of, let's say, almost ferroelectric materials. And I say almost ferroelectric because what happens is that at low temperatures, where your material would normally have a spontaneous dipole moment that is ordered over a long range, in the case of relaxors, this ordering happens over a very short range. So you have clusters or domains. Physicists will be arguing until I die about what's the true exact nature of a relaxor ferroelectric. For those of you who are into magnetism, perhaps the closest thing is a spin glass. Think of it as a dipolar glass, where you have clusters of polarization that are within that cluster coherently oriented, but from cluster to cluster there is no coherence. These clusters, because it's like a glass, below a certain glass transition, they get frozen, and once they are frozen, then you can induce a permanent polarization. You can apply an electric field and it will stay polarized. These materials are very exciting, or very useful. Well, they are very exciting because the physics is complicated and we like complicated things. And they are very useful because they have a very high dielectric constant that is less temperature dependent than a normal ferroelectric. If you remember in barium titanate, this transition was super sharp. Here is more rounded. It is frequency dependent because the ability of a cluster to respond to your AC field depends on the size of the cluster. And because you have a distribution of cluster sizes, you have some clusters that respond at low frequency but not at high frequency. Okay, so at high frequency, you measure a lower dielectric constant than at low frequency. They're also very exciting because these are the ceramics that have the highest electromechanical performance of any ceramic material. by far. Okay, so whether you can call this piezoelectricity or electrostriction, which is another issue that I will talk about some other day, in fact, on Thursday. It's a moot question, but for now, the point is the highest electromechanical performance, the highest piezoelectricity you want that you can have from any ceramic comes from relaxers. So that's the second family of almost ferroelectric materials. This is yet a third family of materials that are very closely related to ferroelectrics, but they are not. They are anti-ferroelectrics. So, ferroelectric, you have all your dipoles, permanent, stable, pointing in the same direction, and you can switch them with an electric field, and you have the typical polarization versus field hysteresis loop. In an anti-ferroelectric, you can think of it as having these dipoles aligned anti-parallel to each other, as you would in an anti-ferromagnet. And what's exciting about them is that if you apply a high enough electric field, you can, say pointing up for example, you can destabilize this downward facing sublattice and make it point up. Okay? Then you so it goes up. Then you reduce the electric field, it goes back to the antipolar state, so you have no permanent polarization, and then the same thing can happen if you point in the other direction. So you have double hysteresis. Yeah.
Can you have different types of antiferroelectrics like you can with antiferromagnets, like G-type and C-type, in the way that they're ordered?
Probably, but I don't know. Antiferroelectrics have been a lot less studied than ferroelectrics, partly because their practical applications are less obvious. There are some, and I will go into that, but they are less obvious, so there's been a lot less work. And I don't know if there's also a fundamental question why they should be rarer. I heard someone, many years ago I saw a theoretical talk about why are there so few antiferroelectrics, but I didn't understand anything, so I couldn't tell you. But that question has been posed, so I don't know the answer. Okay, but I will tell you this, the classic, the archetypal antiferroelectric, the one that we study, is lead zirconate, which is almost the same as lead titanate. So you have a lone pair in the A side, which is the lead +2. And it's just that the zirconium is a much bigger atom than the titanium, and so that gives you octahedral rotations that result in an antipolar configuration. But perhaps this lone pair polarization that is useful for ferroelectricity is also useful for anti-ferroelectricity. Yes? Okay. So applications. So the first and obvious one is, okay, since you have a stable up state and a stable down state separated by an energy barrier, you can call this a 1, and you can call this a 0, and you can make a ferroelectric memory, which you operate with a voltage rather than with a current or with a magnetic field. And that has some practical advantages. Now, the coercive field that you need in order to switch the polarization from up to down, or from down to up, is usually quite big. It's thousands of volts per centimeter. So if you have a bulk single crystal and you want to switch it, you're going to need to crank your voltage up to thousands of volts. Not very useful, because you cannot have a 1000-volt battery in your mobile phone. Right? However, electric field is voltage divided by thickness. So if you make your ferroelectric, instead of being a bulk single crystal, be a thin film, you need a much smaller voltage to achieve the same high electric field. Okay? Because the thickness is in the denominator, you make the denominator small, the electric field becomes big, and that's free. Right? It's a very, very neat geometrical trick. So yeah, the coercive voltage for a film that is less than a micron thickness is typically less than 10 volts. Okay, so it's something that you can achieve with a battery. And that's why ferroelectric memories can be useful, and are useful. In fact, ferroelectric memories do exist. Some of their incarnations no longer exist, so there used to be a ferroelectric memory in the Sony PlayStation 2, and I don't know in what iteration of Sony PlayStation we are now, but I am told that ferroelectric memories are no longer there. However, ferroelectric memories are in some wireless cards, in some contactless cards, like the ones that are like the Oyster card that they use in the tube in London. Okay, so they exist, and it's from a physical point of view, it's a very simple idea. It's your ferroelectric thing, 2 electrodes, and something that you use to apply voltage to the electrode to write. Yeah, so they do exist. Another application of ferroelectrics is pyroelectricity. So since ferroelectrics are, sorry, yeah.
Yeah. For memories, what is the thickness of PZT up to now?
I have no idea. I have no idea. I could tell you what it was 10 years ago. Maybe this is.
We did not go for so much further, but I never know the actual ones.
So
I think it was 90 or 130, but I'm not sure. Nanometers.
I don't know. I can tell you some of the physical limitations that you're going to encounter when you go small.
Yeah.
One of them is that if you go too thin, you can have linkage currents or tunneling currents or shorts of many kinds. You also will have depolarizing field effects, and if I have time, I will talk about depolarization that destabilize your polarization, make it less stable. Now, the critical thickness at which that happens depends a lot on the quality of your film. So, I can give you a figure, but it would be meaningless. But basically, in my lab, I've never been able to measure a stable hysteresis loop in anything thinner than 10 nanometers. Now with a PFM you can go smaller, you can probably go to 5, but in practical terms...
With PZT?
With PZT, yes.
Okay.
Yes. Okay, but it's difficult. Okay, there's another problem in when you make things smaller, which is the lateral dimensions also matter, because the lateral dimensions will define how much charge you can collect when you switch the polarization. If you make it too small, even if you switch the polarization, you're not going to get enough charge for you to measure it, for you to be able to measure it, basically. Okay? Right. Pyroelectricity. So, polarization depends on temperature. Okay, at high temperature, remember your perovskite was not polar, at low temperature it is. In between, the polarization changes. So if you change the polarization, if you change the temperature, you change the polarization, and that gives you a current that you can measure, pyroelectric current. Okay, this is a typical pyroelectric measurement where you fluctuate the temperature and you see the current fluctuating. Where the change in temperature is maximum, the current is maximum. Yeah? And these you can use for making temperature sensors. You can also use it to induce pyroelectric fields that you can then use for field emission, and these turn out to be extremely high, because you can concentrate these pyroelectric fields, and apparently you can even create nuclear fusion with the ions that come ejected by this pyroelectric field. Okay, I think that's a curiosity. I don't think there will be atomic bombs made with ferroelectrics. You needn't worry, but just to say that pyroelectricity is real and it is used. You can also use what I've just described, the polarizability of the unit cell. So at high temperature it's not polar, at low temperatures it's polar. In between, it doesn't know what it wants to be, so it's extremely susceptible. So, which means that the dielectric constant is very large. Large of the order of thousands or even tens of thousands. What this means in practical terms is that if you have a parallel plate capacitor and you put nothing, you measure a capacitance. If you put a ferroelectric with a dielectric constant of 10,000, then you can store 10,000 times more charge, and you can immediately see that this is useful. It's so useful, in fact, that this is by far the biggest application of ferroelectrics. It's not to use its ferroelectricity, it's not to use its polarization, it's to use its polarizability. Okay? A few years ago I kind of did the calculation of how many capacitors there were in the world using BST, so very strong entanglement, which is a ferroelectric line composition. And basically, this would be a Catalan billion or an American trillion capacitors made every year. If you divide that by population, it means that you probably have 1,000 of these. Okay, probably in your pocket. Okay, capacitors. Piezoelectricity is another property of ferroelectrics. So, if you remember the unit cell, let me go back here. The unit cell is not just polarized, it's also distorted along the polar direction, which means that if I apply pressure and change the shape, I'm going to change the polarization. Or vice versa. If I crank up the polarization, I'm going to induce an additional deformation on my sample. Yeah? So, this is piezoelectricity. You probably knew about this already. If you take a piezoelectric material and you push it, you change the shape of the unit cell. That changes the polarization, and when you change the polarization, you get a voltage. Okay? You generate some bound charge that will give you a voltage. I will talk in a second about what I mean by bound charge. Or vice versa, I can apply a voltage, and my material will respond by deforming in the direction of the electric field that I applied. Yeah, and this is, again, super useful for sensors, for pressure sensors, and for actuators. This was probably the very first application of ferroelectrics, was to make sonars in the Second World War. So at the same time that the Manhattan Project was going on in Los Alamos, in the MIT there was another project that involved designing sonars, and that's where barium titanate was discovered, for detecting the German submarines. Which is a bit of a not such a nice story. Our very first application of ferroelectrics was for war. However, the exact same technology is also detected to detect babies. Okay, a baby, think of a baby as a submarine inside the belly, and the idea is the same. You generate a pressure wave with the piezoelectric, the echo bounces back, and you detect the echo with a piezoelectric again. So the piezoelectric is used both for generating the pressure wave and for detecting the pressure wave that comes back to you. Okay? And there's a whole bunch of other actuators and sensor applications that are based on piezoelectrics. Those are some of the applications that are already in the market, that do exist, and that people actually pay money for them. Then there's some other more futuristic ones that I will mention briefly. But before I mention them, I need to say something that is important for ferroelectrics, which is that until now, in everything that I've said, without saying it explicitly, I've implied that ferroelectrics are insulators, are dielectrics, and that means that if I apply an electric field, I can stretch the unit cell, I can separate the charge within the unit cell, but I cannot make charge travel. Okay? Any charge that is there is bound to its unit cell. In fact, they are not perfect insulators. They are usually wide bandgap semiconductors, or at least the perovskite ones. So the most famous ones are Bismuth Ferrite, will be familiar to some of you, that has a bandgap of about 2.5 or 2.7 eV. PZT, barium titanate, strontium titanate, all of these things have bandgaps of the order of 3.5 volts, 4 volts max. Okay? They are semiconductors. As one thing that you need to know, the other thing that you need to know is that if you do nothing to a ferroelectric, ferroelectricity is quite unstable in the sense that the polarization points this way. Okay, each of these things is a unit cell. Here I have a whole bunch of positive charge that is creating an electric field that emanates out, and here an electric field that goes in. Okay, and this electric field covers the entire volume of the universe, if you want. It has an electrostatic cost. And this electrostatic cost actually fights against the very existence of this polarization. And that's why this is called the depolarizing field. Now, in order to screen the depolarizing field, what you do is you put an electrode, and the electrode can freely, very cheaply supply some charge, and that you can put some negative charge on the electrode that will compensate the positive charge, and you can put some positive charge here that will compensate the negative charge. The screening, however, is never perfect. Never. It cannot be, because even in a perfect, almost perfect electrode, there's what's called the Thomas Fermi screening length, which means that there is, if you want, some space where in between where the charge is, where the charge of your electrode finishes and the bound charge of your ferroelectric starts. So in this finite amount of space, there's a very big depolarizing effect. Okay? Big or small, but it exists. You can never completely get rid of it. You can, however, use it. You can use this depolarizing field to modulate, for example, the charge density of a material that you attach to it. Okay? So you could use, I think this morning we heard about strongly correlated electron systems. You can put a manganite in contact with your ferroelectric, and depending on the orientation of the polarization, that will create an electric field that's pointing down or up that has to be compensated by free charges. Those free charges will be provided by the manganite, and in doing so, those free charges will no longer be free, which means that the conductivity of your channel will go down. Okay, so you can modulate the conductivity of the channel using the polarization, the ferroelectric field emanating from your ferroelectric. Yeah, that's a field effect transistor by using oxides. With the, if you want the added, I don't know if it's an advantage or a disadvantage. In this case, if you want to publish in Nature, you say it's an advantage. If you say it can stay written, so it's not just a transistor, it's not just a field effect transistor, it's also a memory. Okay? Good. Other interesting things about ferroelectrics, that's another futuristic application that does not exist yet, but people is hoping that it will exist, is to take advantage of the fact that the crystal lattice of ferroelectrics is asymmetric, which means that if you shine light into a ferroelectric, and it has to be light bigger than the bandgap, 3.5 volts, so you need to, in this case, it has to be UV light. If you want to do photoelectric experiments with the normal ferroelectrics, you need to use UV light. Okay, that aside, once you shine light, if the light gets absorbed, you can create an electron-hole pair. Normally, an electron-hole pair will recombine more or less instantly, or on average, it will recombine wherever it's been created. But because the unit cell of ferroelectrics is asymmetric, electrons have a tendency to go one way, and the holes have a tendency to go the opposite way. Okay, so you can separate the charge just by virtue of the fact that it has been created inside an asymmetric lattice. This is called the bulk photovoltaic effect. It's a bulk effect. It does not depend on an interface junction between two semiconductors. Okay? You get it just for free from the fact that you have a lattice that is asymmetric. Because it's not an effect due to band bending, by something intrinsic to the lattice, it's not limited by the band gap of your material. So whereas the normal photovoltaic effect is basically limited by the band gap of your two semiconductors that you're using in your solar cell, in ferroelectrics this is not the case. You can get photovoltages that are huge. Okay? This is an experiment that we actually did in our lab. Ferroelectric thin film with one transparent electrode, you shine light, and the open circuit photovoltage is tens of volts. You can even measure more than 100 volts. This experiment was done also about 30 years ago with lithium niobate on a single crystal, and I think they measured 1,000 volts. Huge. That's obviously bigger than the band gap. And in fact, if you divide the voltage by the thickness of the film, and remember this is a very cheap geometric trick, then the photoelectric field can be huge, right? Almost 1 million volts per centimeter. There is a catch, and the catch is that ferroelectrics are not good conductors, so even though you can get huge voltages, you get very, very small currents. Okay, so this is not yet, in any shape or form, a useful technology. But people are hoping to be able to increase now the current. Yes?
Would we expect some short circuit current by shining a below current light?
Would I expect a short circuit current? I guess yes. Yes, partly it will be small, but you could get it for a couple of reasons. One is that you have some defects that locally, some defect states, and the band gap for those, the excitation energy for those defect states is much more than the band gap. So for oxygen vacancies, it's typically 1 eV. That's one thing. The other thing is your light is never perfectly monochromatic. It has a tail, so maybe the spectral tail can reach into the band gap too. So yes, you can measure some current, but it will be pitifully small. I mean, it's already small when you use the full-on above band gap light. Below band gap, it's going to be very small.
What's the limitation of the thickness of the sample you used?
This was, I think this particular sample was 1 micron, but I don't think there's any special limitation. I can't think of any. Yeah?
Yeah, I have a question. You mentioned that the conductivity is relatively low, and that's why you have low currents in these kind of devices. What are the ideas to improve that? I mean, how can people improve the current?
I think if I knew the answer to that, I would be a rich man.
What are the parameters that you need to address to improve that in this material?
You know, okay, so there's a couple of schools of thought. One is that you can just reduce the band gap of your ferroelectric, so try to get a ferroelectric that has a band gap instead of being 4 volts or 3.5 volts, be 2.5 volts, as in Bismuth Ferrite, or even smaller. That's one possibility. The other thing is to make something in tandem. So you have a ferroelectric in parallel with something that is semiconductor. You induce the big photovoltage in the ferroelectric, and then this big photovoltage from the ferroelectric will drive a current in the semiconductor. That's another possibility. That I think has a bigger chance of working, so the tandem idea. The idea of making your ferroelectric itself more conducting, for me, it's probably doomed. And the reason why I think it's doomed is, okay, you'll get a bigger current, but then your voltage will go down, because in fact the intrinsic property, in the bulk photovoltaic effect, the intrinsic property is something called the shift current. So you shine light, you get a current. That current, that current multiplied by the resistivity of your material will give you the photovoltage. Now, if I reduce the resistance, I get a bigger current, okay, but I also get a smaller voltage, because the voltage is current. Well, no, sorry, no, I don't get a bigger current. The current is what it is. Yeah. I get a smaller resistance, but the product of current time resistance is small, so the photovoltage is going to be small. Okay, so I personally think that making ferroelectrics that are more conducting, it's a trick where what you win on one side, you lose on the other. It's just, but this is not a fact. That is just my opinion. Right? Yeah. Okay. Oops. Electrocaloric effect is another area in which people are doing research. Brahim, in fact, is there. Normally he gives talks in this school. This time he's not, so I'm going to give the talk for him. But I'm only going to give one slide. And the idea is the following. In a ferroelectric, or any material, okay, in a polar material, if I apply an electric field, I can align the dipoles. If I align the dipoles, I reduce their entropy. And if I reduce their entropy, they will release heat. So the material will become hot. I apply voltage, things become hot. That's the normal electrocaloric effect that you see in ferroelectrics. A cool thing that happens in anti-ferroelectrics is that you get an anti-electrocaloric effect, which is that when you apply your voltage, your material, instead of getting hotter, it gets colder. And that's pretty funky when you think about it. I'm putting energy into my system, I'm applying a voltage, and my system is getting colder. And the reason why that happens is debatable, but the bottom line is that somehow you must be increasing the entropy. And of course, if you think of it, this is Jim Scott's idea. If you have an antipolar lattice and I apply a voltage, say, pointing that way, I'm going to destabilize this sublattice, and that increase in entropy is what requires absorbing heat, so the thing becomes cold. Yeah? Okay. So that's one area of research. The other area of research specific of antiferroelectrics is for energy storage. Okay? If you think about the work that you need to do in order to charge a capacitor, it's basically the integral of the electric field times the polarization. So it's basically whatever is between the vertical axis of polarization and the horizontal axis of electricity. Okay? So this area will be your work in a linear dielectric. In a ferroelectric, the charging, this is actually a wrong image, the charging electricity would be this, okay, the area between this line and this line. However, when you switch off the voltage and you go to here, this is what you get back. So actually the hysteresis means that you've lost some energy. In an antiferroelectric, by virtue of the funky shape of the hysteresis loop, this shaded area is much bigger, which means that antiferroelectrics are good for storing electrostatic energy. Okay? Okay. And multiferroids, I should have mentioned that in the kind of ferroelectric-like materials. Multiferroics is another area of research. I'm not going to talk much about them because I think there's going to be a talk about them later this week or next week. But basically, multiferroic is a material that has at least 2 ferroic order parameters, and you immediately think of ferroelectricity and ferromagnetism. There's also something called ferroelasticity, which is basically a hysteresis relationship in the stress-strain relationship. That sounds very complicated, but basically what it means is that if you look at lanthanum aluminate, for example, maybe you're familiar with this substrate, you will see that it has these funky twins because it can shear in one direction or it can shear in the other direction, and between these 2 shearing directions there is an energy barrier. Okay, so if you measure the elastic response, it's hysteretic. That's a ferroelastic. So you can have ferroelectric ferroelastics, and you can have ferroelectric ferromagnetics, and you can have all combinations of this. The one that people is excited about is the combination of ferroelectricity and magnetism in the same material. The idea being that if you had something that was at the same time ferroelectric and ferromagnetic, and the 2 things were coupled, you could write your magnetic memory by applying a voltage. Okay, you apply a voltage, that changes the polarization, and if the magnetization is coupled to the polarization, the magnetization will also switch. Okay, so you can write it at a low energy cost because you're just applying a voltage, which in a thin film is small, remember? And then you can read it non-destructively using the usual machinery of spintromics. Okay. These are rare. I think I'm not even going to discuss why they are rare. Just take it from me. There's very few materials that are truly multiferroic. In fact, the standard one is bismuth ferrite, and bismuth ferrite is not even a ferromagnetic material, it's an anti-ferromagnetic material, and there's some reasons why that is the case. They are rare, and the jury is still out as to whether we will manage to make such a multiferroic memory. If we have time at the end, and you want, you can ask me as to why we think these materials are rare. Okay. Right, part 2. I was very keen on getting to this. Experimental characterization of ferroelectrics and multiferroics. The basic principle, and I put principle because there's lots of principles, but there is one that is very important, and important artifacts. I'm not going to talk about all the ways in which you can measure ferroelectricity, because there's many of them. I've mentioned Raman, there's piezo response force microscopy, there's a whole bunch of tools, but the basic one is to measure a hysteresis loop. And the way it works is like this. You have your ferroelectric with your electrodes, okay? Remember, if you have your polarization pointing up, that's here, okay, pointing up, you have some negative screening charge here, some positive screening charge here. Fine, that's stable. If I apply a voltage and I switch the polarization from being up to being down, then now the screening charge that I need here has to be positive, and the screening charge that I need here needs to be negative. If I have an amperemeter connecting these 2 things, I can measure the flow of charge going from here to here, when you go from this situation to this situation. This is to say, I am not measuring polarization. I am not even measuring charge. I am measuring changes in polarization, and that's very important. I believe it's almost a universal truth that polarization per se is not a measurable quantity. You can only ever hope to measure changes in polarization. I think, maybe David will correct me if I'm wrong, this is true even for theory. So to quantify polarization, you need to do it in reference to a lattice that is non-polar. Or if you do X-rays, you say, okay, these are the atomic positions, this gives me the polarization. This gives me the polarization by comparing the atomic positions with respect to what would be the centrosymmetric lattice. Okay? I think that's true for theory. It's definitely true for experiments. You can only ever measure changes in polarization, which you measure in the form of currents. The problem is, whilst changes in polarization will give you a current, and this is called the displacement current, not all currents come from ferroelectric displacement. Okay? And your machine is blind, your machine is dumb, it only measures current, and if you don't know what's going on, you might believe blindly, okay, this is polarization, but it might not be. Why? Because if your material is a semiconductor and you apply a voltage, you may switch the polarization, but you may also induce some leakage current. Okay, and this leakage current has nothing to do with ferroelectricity. And you have to be able to distinguish the two. This is very, very important for this audience because I presume some of you are not coming from the ferroelectrics area but from photovoltaic area. You're interested in photovoltaics. All photovoltaics are semiconductors, so if you apply voltage to them, they will give you leakage, for sure. And some of you are interested in multiferroics. All the multiferroics that I know have even smaller band gaps than the normal ferroelectrics, so they are also very leaky. Okay? So if you come new to ferroelectrics and you measure a hysteresis loop, before you publish, please ask someone who works in ferroelectricity. Okay? This is very important, really. Otherwise, people like Jim Scott will ridicule you, will take the piss out of you. Okay? So this is a typical hysteresis loop that you can measure with the commercial radiant. Doesn't matter which one you use. In most labs we have a machine called the radiant box. It's a black box, in more senses than one. And it gives you charge as a function of voltage, but of course the software doesn't tell you that this is charge. It tells you that this is polarization. This is basically it's integrated charge divided by area, and you call that polarization. But it may not be polarization, because this very hysteresis loop was measured on the skin of a banana. Yeah, I can testify that. I was there. I saw it with my very own eyes. Okay? So you take the skin of a banana, you put electrodes, you measure a hysteresis loop, and you will see hysteresis, which obviously has nothing to do with ferroelectrics. Now, because Jim has a bit of a sense of humor, he also measured the hysteresis loop of a material called barium sodium niobate, which, if you do the acronym, is banana. This is the real ferroelectric banana. This is the non-ferroelectric banana. Okay. Okay, and this comes from the fact that when you measure charge, you can measure charge that comes from the switching of this polarization, but you can also measure charge that comes from the conductivity times the electric field times the integration time. Okay, and I have to stress this effect can be very misleading, can be very deceptive. It can look like real hysteresis. If you do the theoretical hysteresis curve for two pure Schottky diodes back to back, this is what you should get. Okay? And this does look a lot like a ferroelectric hysteresis loop. So don't just trust the shape. Even if it looks very ferroelectric to you, be careful. Okay? This is a classic example. We actually measured that in our lab. This is ytterbium chromite hysteresis loop. First time we saw this, we thought, happy days, we have a new multiferroic. But then we did what's called a pond measurement, and all the random polarization was actually zero. Okay? So they can be very deceptive. So how do you detect whether what you have is an artifact or not? One way, if you have the radiant black box, it's called the pond measurement, positive up, negative down. So what you do is you apply a negative voltage to pull everything pointing down. Then you apply a positive voltage to switch it up, and you measure the charge when you switch. Then you apply another positive pulse, and you measure the charge again. Now, because this has been switched, any charge that you measure on this second loop cannot be due to switching. It will be all the rubbish. It will be all the leakage. It will be the dielectric contribution. Okay. So then you subtract this charge from this charge, and what you're left with is a proper switching charge. Okay. So this contains everything, switching plus leakage. This one, because you've already switched, only has the leakage. And then you do the same thing for the negative voltage. Okay. And if you do this on a real ferroelectric, like ZT, after you switch, you get rid of the dielectric term, which is what gives you the slope in the hysteresis loop. And this is what a pond loop looks like in proper ferroelectric ZT. And this is what our pond loop looks like on our fake ferroelectric. I hate how the word fake has been spoiled by Trump, but anyway. Never mind. Okay, if you don't have the black box, if you don't have a radiant, and you cannot do pond loops, there's still hope for you. There's still other things that you can do to distinguish real ferroelectricity from fake ferroelectricity, which is look at the frequency dependence. Okay, the leakage charge depends completely on the integration time. So more time you are measuring, more leakage is flowing through your capacitor. Whereas the switch charge does not. Once you've switched, it's switched, that's it. So if you measure your loop very slowly, you'll see a very fat hysteresis loop that contains the switching contribution plus the leakage contribution. If you measure very rapidly, you will only have the switching contribution and you'll have much less of the leakage one. Yeah? So if your material is leaky, try to measure it as quickly as possible. The bottom line. Yeah? I have no idea how we are for time.
Oh, I think we're 1 hour in.
Okay, right. Basically, whenever you're bored or whatever, you stop me. But I can talk with the.
This consideration about the velocity of the measurement means that ferroelectric switch is very rapid.
Yes.
And how is the typical time scale for very rapid?
Well, at room temperature, the thing is, switching itself has very complicated physics, because even though an individual dipole can switch in the gigahertz regime, switching normally proceeds by nucleation of an antiparallel domain that has to grow and then expand. And that growth and expansion depends on temperature. So in fact, at low temperatures, it can be quite slow, but at room temperature, this happens within microseconds. Basically, it happens faster than the electronics. The switching speed is limited by the speed at which you can provide charge to your ferroelectric. But yeah, if you go to very low temperatures, there's an exponential of Arrhenius law, and because it's exponential, it can get slow very rapidly. So at low temperature, ferroelectrics can become unswitchable, basically because things are happening so slowly. The intrinsic coercive field is very, very large, so you need to rely on domain movement, and if the domain walls are frozen, then you won't be able to switch. Okay. But for the sake of practical applications, room temperature, microseconds. Yes? Okay. There's another important artifact that I want to stress, which is a colossal relaxer-like dielectric constant. And this is also ubiquitous in the literature. Every time a new field becomes fashionable, like multiferroids or photovoltaics, someone claims to have seen a relaxer-like giant dielectric constant in their material, which is nothing of the sort. To remind you what a relaxer dielectric constant looks like, this is it. Okay, so you have something that has a temperature dependence, but it's kind of not a very sharp temperature dependence, and the maximum of the dielectric constant shifts as a function of frequency. That's one of the features of relaxers. Another important feature, and this is the one that you will use to distinguish between a true relaxer and a fake relaxer, is a frequency dependence of the dielectric loss. Okay? In true relaxers, the dielectric loss goes up as you increase frequency. That's quite unusual. For the artifact that I'm going to describe now, the opposite is true. The losses go up as frequency goes down. Okay, so classic example. This is a calcium copper tightened. This became, very hot topic a few years ago. Not such a few years ago, 2 decades ago. People were measuring the dielectric constants of the order of hundreds of thousands. Would you think good for making capacitors, right? And they say that this was a type of relaxer. In fact, it's not. Okay? This is something called the Maxwell-Wagner effect, which I'm going to describe to you very briefly. Okay? This is just to stress that you can have something that looks very relaxer-like, but it's just a Maxwell-Wagner effect. Okay? And this is a calculation that I did that you can do. You can do this calculation just using Excel. It's extremely simple. So how does it work? Imagine that your dielectric material is not a perfect dielectric, it's a semiconductor, and we know that all dielectrics are ultimately a bit semiconducting. They have finite band gaps. Point 1. Point 2, imagine that your material is not homogeneous. So basically you have two components, maybe the interfacial component and a bulk-like component, or you have something that is mixed in some way. So you have some areas that are more conductive than others. The simplest way to model this two-component leaky dielectric is by what's called the Maxwell-Wagner circuit. These two leaky to lossy capacitors in series with each other. If you calculate the dielectric impedance of this circuit, this is just an equivalent circuit model, you will see that it depends on these taus. Taus basically are resistance times capacitance time constant of the two elements. Okay. This looks like a very complicated equation, but the physics is actually much simpler. If you measure at super high frequency, high enough that the leakage current does not have time to travel across your semiconductor, then the dielectric response that you're going to measure is a true dielectric response. If you measure at a lower frequency, however, it might happen that one of the two components in your circuit allows the current to travel across it because it's leaky, right? And in that way, what you have is basically like an extension of the electrode. The new electrode is no longer here, it's here. Your dielectric component is no longer the entire thickness of the capacitor, it's only the thickness of the element that is insulating, or that is more insulating. And because capacitance goes as 1 over thickness, the capacitance goes up. If that very high capacitance you multiply by the total thickness of your capacitor, you think that you have a very high dielectric constant, but it's not. It's just an artifact that comes from the fact that the actual insulating part of your sample is very thin. Is that more or less clear? Yeah? Okay. So that explains the huge dielectric constant. It also explains the frequency dependence, because whether the charge or not flows depends on whether you're measuring fast or slowly. It also explains the temperature dependence, because at high temperatures things are more conducting, so it's easier to reach into this regime. So let me go back. So at high temperatures, you very easily reach into the high capacitance regime. It's a high capacitance, but it's not a high dielectric constant. Yeah? And of course, you can modify the capacity if of those two resistive leaky elements, the resistance of one of them depends on a magnetic field. So if say you have a magnetoresistive material, you will measure a magnetocapacitance, but it will not be a magnetoelectric effect. Okay? It has nothing to do with magnetoelectric coupling. And if your material is photovoltaic, the same thing will happen. So if you shine light on your material that is leaky, the light will make it even leakier, and so your capacitance will go up, and so your apparent dielectric constant will go up, but this is not a real dielectric constant. Okay? So if you're going to measure the dielectric properties of photovoltaic materials and the response to light of those dielectric properties, be aware that you're not measuring a dielectric response, or not only a dielectric response. Yeah? This is perhaps the most important thing that I'm going to explain to you today. If I don't say anything else, I consider my job done. Right? So bottom line is, hysteresis loops can look very convincing, but if your material is semiconducting, they can be fake. And likewise, you can have colossal dielectric constants in materials that are semiconducting, but they have nothing to do with dielectricity. Okay. Right? Ways in which you can distinguish. You can, for example, change your electrode. If your capacitance depends on your electrode, it means that it's an interfacial effect and not a bulk effect. Or you can change the thickness. Okay? If you change the thickness of your capacitor and the dielectric constant doesn't change, it means that the dielectric constant is not coming from a bulk effect, it's coming from a barrier, the thickness of which you are not changing. Okay? Okay. And you can look at the loss, and this is what I was saying earlier about the relaxers. So in relaxers, as you increase the frequency, the dielectric loss goes up. So as you decrease the frequency, the dielectric loss goes down. This will be the shape of the relaxation peak in a relaxer or in any dielectric material. In a material that is leaky, that is not a relaxer, at low frequencies, your material is becoming more lossy, so your losses go up. Okay? So the frequency dependence of the dielectric loss is the absolute bulletproof proof. Yeah? Okay. Right. Landau theory, strain engineering. I don't know where to go into this. How are we for time? No? We're all right? Okay. Bit of Landau theory. If you fancy that. Wait. Do you have any questions before I move into that? No questions. You're either too sleepy or I'm a very good teacher. Okay, so the minimum that you need to describe a phase transition. Okay, Landau theory starts with a thermodynamic potential that describes the energy of your material as a function of the other parameter, which in a ferroelectric obviously is the polarization. It's essentially a Taylor expansion. And what you put in the Taylor expansion will determine the solution. Okay, now this thermodynamic potential needs to be able to describe both the high symmetry phase of your material and the low symmetry phase of your material. Okay, so if the high symmetry phase of your material is cubic, is centrosymmetric, then in this Taylor expansion you cannot have any odd parity terms. Okay, so if I invert space, the free energy cannot change. In the cubic phase, once you are in the polar phase, it will obviously change, but in the cubic phase it cannot. And since this has to describe both, I can only put terms like p squared, p fourth, p6. I cannot put p or p cubed. You can break that symmetry if you apply an electric field, and then obviously the coupling between the electric field and the polarization is linear. And okay, if the polarization is parallel to the electric field, the energy will go down, and that's why you put a minus here. Okay, so this is more or less how it works. It's Taylor expansion, and the powers that you put here and the signs that come here come from symmetry considerations. Okay, so this comes from symmetry considerations, this comes from energy considerations. Yeah? Okay. Even the sign of these things also come from thermodynamic considerations. Imagine for a second that beta was negative. If beta was negative, it would mean that my energy would get lower and lower as I make polarization bigger and bigger, which means that my material would have the most favorable, energetically most favorable state would be having infinite polarization. Basically, my material would explode. So that's not going to happen. All right? We need beta to be positive for a second order transition. Alpha can be positive or negative. If it's positive, then both of these things are more or less parabolic and pointing up over in this state. If alpha is negative, then for small values of p, the curvature is negative, and then eventually when p4 takes over, things become positive again. So you get a double graph. Okay, that's just maths. All right, and in between, if you have a continuous second order transition, you have a state where the barrier between here and here is 0, you have an infinite dielectric constant. Okay, and the inverse permittivity goes to 0. Okay, you can do the mass of this. You probably did already do the mass of this in, a university, hopefully. One thing that is worth noticing is, okay, you get the equation of state by minimizing the free energy with respect to the polarization, gives you this. The derivative of the electric field with respect to the polarization is the inverse susceptibility, which is this. You notice when you do this derivative, the electric field term basically disappears. And this is another way to say that the inverse susceptibility is the same as the second derivative of the free energy with respect to the polarization. Or if you want, the curvature of this. The curvature here is positive, here is negative. And I mention this because this is something that is becoming very, very fashionable right now, which is something called negative capacitance. Now the physics of negative capacitance is more complex than I can even understand fully myself, never mind explain. But one of the things that I can say is that from a mathematical point of view, if you were sitting here, you would be operating in a landscape where the capacitance, or if you want, the dielectric constant is negative. Yeah? Of course you cannot sit here, being here is unstable, the stable states are this and this, but at least in a transient way, if you want, you can be in a negative capacitance state. Yeah? Okay. Nobody has killed me yet for saying that. I'm very relieved. First order phase transitions, the maths is similar. It's only that now the term that is positive is gamma. Okay, so you have a P6 term, and it has to be positive because otherwise remember that your polarization will go to infinite. But if this, as long as this gamma is positive, now beta can be negative. Okay? And now depending on, so let's make this one negative, this one positive, and this can be positive or negative depending on temperature. And that can give you all these regimes. So when everything is positive, your material is definitely paraelectric. When these two are very strongly negative, you are definitely in the polar phase. And in between, you can have a metastable polar phase, or you can have a metastable non-polar phase, depending on where you are cooling or heating. And that's why in first order phase transitions, you have some hysteresis. So when you measure the polarization of the structure as a function of temperature in a ferroelectric, if you see hysteresis, it's an indication that the phase transition really is first order. And it so happens, and in most ferroelectrics that I know, in fact, in all the ferroelectrics that I know, the phase transitions are slightly first order. Okay, they are almost second order, but not quite. They are a little bit first order, and you always see a little bit of this hysteresis. Okay. Sorry, yeah?
I have a question to this. If you include like p to the power of 8,
Yes?
you still can say like if beta is smaller than 0 is first order and it's bigger than 0 is second, or do you have like a different
Okay. I would deflate that question towards David. So, first of all, you need to include p to the power of 8 if you want to describe symmetries, sophisticated symmetries, like say monoclinic symmetries. So you need that. As to whether including a p8 term implies a first order phase transition, no, it doesn't. Whether it's first order or second order, it will depend on whether one of the lower order is negative. I cannot tell you whether it needs to be the beta term, the one that is negative, or the gamma term that is negative. That I don't know. Maybe David knows, maybe he doesn't. I don't. Okay. So P8 terms we need to describe highly asymmetric phases like monoclinic phases. And as to the sign of beta and gamma, I don't have an answer. Sorry to disappoint. Yeah? Okay. Then, okay, so that's just the polarization. You can then add the stress or the strain and the coupling between the stress, in this case, sigma, and the polarization. And for perovskite ferroelectrics, the lowest term that you need to include here, or the lowest term, coupling term that you can include is strain or stress times p squared. Okay? And remember, it has to be p squared because it has to describe also the high symmetry phase of your material. You think, okay, if it's a piezoelectric material, I should be able to put p times sigma here, so polarization times strain here, linearly coupled, as you would expect in a piezoelectric. But your free energy has to also describe the cubic phase, so the polarization has to be squared. Yeah? Then you do this, you resolve, and what you find is that the term multiplying p, that used to be alpha, now is alpha minus this thing, the electrostrictive coupling term, the Young's modulus, some constants. Okay? And the term that was multiplying p fourth now has been renormalized also. So both the alpha and the beta have been renormalized. What does that mean? Well, alpha, I forgot to mention that, alpha is the one that gives you the temperature dependence. It's the one that tells you whether you are in the paraelectric phase or in the ferroelectric phase. Alpha is the Curie constant times T minus Tc. It's the one that gives you the critical temperature. So now the strain, epsilon here, is changing alpha, so it's changing the critical temperature of your ferroelectric. And beta is the one that is telling you whether something is first order or second order. So you can start with something that is first order, so where beta is negative, but as soon as you put the strain coupling, notice that this is the Young's modulus, which is positive, this is Poisson's ratio, this is positive, this is the electrostrictive coefficient, which may be positive or negative, but it's squared, so it's also positive. This is positive. Typically, this is not only positive, but bigger than beta. So even though most ferroelectric phase transitions are first order in bulk, when you make it in the form of thin films, the epitaxial clamping turns them into second order. Okay? So you can use strain to change the order of the phase transition, or to change the critical temperature. That has been done. Okay? You see? And this is how it works. Okay? You take your substrate, you take your ferroelectric film, you try to grow this epitaxially here, you force some constraint, you stabilize the ferroelectric phase at room temperature, even if your material would not have been ferroelectric at that temperature. Okay, and this really works. So you take barium tinnate, the critical temperature of barium tinnate bulk is about 130 Celsius. If you grow it on a scandate substrate, the critical temperature is of the order of hundreds of degrees Celsius. Okay, so it's a really powerful tuning of the transition that you get. And then you can get as sophisticated as you want, or as you can, which I can't, but people cleverer than me can. So you can use Landau theory to calculate what kind of strain should you impose onto your ferroelectric to induce different polar symmetries that are not just your classic tetragonal up and down, but tilted polarized states. Okay, and these are the kind of games that people play with ferroelectrics, and it's called strain engineering. And since this is an introduction, you should know about it. Okay. Yeah. So this is the idea. You take your substrate. I have my tetragonal ferroelectric that I want to grow on this, but this has a bigger lattice parameter than this. So what happens is that the polarization tilts, and that way it adopts a lattice parameter that is kind of closer to that of the substrate. Yeah? Okay. In reality, however, if you try to play this game, what you will find is that your material breaks into domains. So there's a fine line between the changing the symmetry of your material. Okay, so something that would have liked to be tetragonal, you're asking it to be monoclinic. Sometimes you manage, and it will be monoclinic, but sometimes what it will do is it will break into tetragonal domains such that the average lattice parameter coincides exactly with the lattice parameter of the substrate. And then you haven't changed the symmetry, you just changed the domain configuration. And this is something you should know about ferroelectrics, is that they have domains. And there will be a talk about domains by Lane Martin, I think, on Friday. But just to warm you up for it, when you go, if you take the simplest possible ferroelectric structure, so going very entirely from the cubic state to the tetragonal state, you can go tetragonally horizontal, or tetragonally vertical with polarization down, or up, or polarization down. All of these are equally probable. They have exactly the same free energy. And if they have exactly the same free energy, when you cool down from the non-polar state to the polar state, you will have some regions like this, some regions like that, and some regions like that. And wherever they meet, that's called a domain wall. Okay? So a region that is homogeneously polarized is a domain, where a domain meets a different domain, you have a domain wall. This is a purely ferroelectric domain wall, where the polarization is switched by 180 degrees. This is not just ferroelectric, but also ferroelastic domain wall, where the vertical polarization meets the horizontal polarization. Yeah? I'm saying this because this is a fairly hot topic in ferroelectrics at the moment. And it's a hot topic because domain walls have completely different properties from those of the domains they separate. Okay. Trivially, if you have a domain wall separating down polarization from up polarization, the polar state of the domain wall is zero. Has to be zero, at least along the polar axis. So you have a non-polar entity embedded within a polar matrix. So you can trivially see that the domain wall has different properties. That's true for ferroelectrics. For anti-ferroelectrics, you have kind of the opposite. So if you have your up, down state, and then you have the next domain being down, up, this antiphase boundary is polar. Okay, you have two dipoles that are not compensated, even though the material itself is non-polar. Okay, so these are trivial examples. You can get more sophisticated because there may be more than one order parameter in your material. It can be ferroelectric and ferrodistortive, when you have octahedral rotations, or magnetic. And when you transition from one polar state to the other, so one polarization to the other polarization, you may take a detour in the free energy space. You may take a detour along a place where the secondary order parameter, which was suppressed, can emerge. Okay? And again, you can calculate all of this from Landau theory, but this is to say, in multiferroic materials, and most ferroelectrics are multiferroic because they're also ferroelastic or ferrodistortive or have a suppressed ferrodistortive phase, you can have emergent properties that exist only in the domain wall. And this is very exciting. Importantly also, as you make your film thinner, the energy cost of creating a domain wall becomes smaller, so you can have more and more domain walls. Basically, this is to say that domain size scales with film thickness. So the thinner your film, the smaller your domains, and more, you'll have more and more domain walls. So the properties of domain walls may affect the overall behavior of your sample. Okay. I'm not going to talk about photovoltaics because I've already discussed this. I've already discussed this. Negative electrocaloric effects. Oh yeah. Okay, this is the section about trending topics. So domain walls was one. Photovoltaics is another, which I've covered. Electrocaloric effects is another. And I only wanted to show this because it's a cool movie of what happens to an antiferroelectric when you apply a voltage. So you basically switch the polarization, and as you switch it, you create like a cold front that sweeps across your sample. And the temperature changes that you can get here are pretty big, of the order of 5 degrees, which is, I am told by those who know about electrocalorics, that is something big, useful. Now 5 degrees by itself is not useful. The thing is you can switch many times and get 5 plus 5 plus 5. Okay? So you can get, and of course when you switch off the voltage, the thing goes back to the antipolar state and returns you the temperature. So you want to do that, you want to switch inside your fridge, then take it out and switch off. Okay, so domain walls, what else have I covered? Negative capacitance. So I'm now in the section where I'm going to blurb about things that are fashionable in ferroelectric research. I mentioned earlier negative capacitance, which is a hypothetical state that would exist if you could stabilize your material here. If you calculate the electric field as a function of polarization, has this S shape. You cannot access this normally because when you switch polarization, you switch from the minus polarization to the plus polarization. But if you could access this area here, the derivative of the electric field with respect to polarization is negative. Why is this useful? Well, it's useful because when you're just on the cusp of going from the plus polarization to the minus polarization, any small voltage is going to give you a ginormous polar response that you can then use to modulate the conductivity of a channel. So people who know about transistors, and I'm not one of them, believe that you can use this negative capacitance effect to achieve higher performing transistors. Transistors where you can get a much bigger gain than you would get by normal semiconductor processes. You can overcome what's called a Boltzmann theory. Okay, that's it. And that's it. So that takes me to the end of my talk. We'll be glad to hear. I've tried to cover quite a few things, from basic principles to applications to, let's say, trending topics, negative capacitance, whatnot. But there's a few things that I want you to take home. One is that ferroelectrics really are very multifunctional. Okay? They have piezoelectricity, they have paraelectricity, they have very high capacitance, they have interesting optical properties that I haven't even touched, and all of these things are used in actual devices that you can buy. The coupling between polarization and structure is inherent because all ferroelectrics are piezoelectric, and you can use that both as a function in itself, as in you can exploit the piezoelectricity, or as a way to tune the properties of your ferroelectric thin film via strain engineering. Okay? The ferroelectric characterization is a bit of an art. You need to know what you're doing. And if you don't know what you're doing, if you're new to the field, really I strongly encourage you to talk to someone who does. Okay? Especially be aware of ferroelectric hysteresis loops and super high capacitance if your material is semiconducting, if it's leaking. And finally, that at the nanoscale, things get even funkier because you have depolarizing fields that you can use for negative capacitance applications, perhaps. You can use them to induce the appearance of domain walls, and domain walls are also cool, and so on and so forth. So ferroelectrics are already quite, I think, interesting and cool at the macro scale. When you go nano, they get even funkier, and there will be a talk by Celine Lichtensteiger, who is going to tell you more about that next week. And that's all. Thank you.